In this section, we're going to describe how molecular orbitals are used to share electrons in molecules. So we'll start with the molecule methane, which is CH4. And if we look on the left-hand side, we've got a structure that shows us the pair of electrons that's being shared between carbon and each of the hydrogen atoms. Over on the right-hand side, it's giving us more of a three-dimensional model of that molecule. And we know that when we have four bonding pairs of electrons and no lone pairs of electrons around a central atom, we're looking at a molecular shape which is tetrahedral. So we want to talk about the valence orbitals that are involved in bonding. And when we look at hydrogen, hydrogen uses its 1s orbitals in bonding, whereas carbon uses its 2s and 2p orbitals. So if we look at this particular picture, just as a reminder, we've got the s orbital up in the upper left-hand corner, and we've got the three mutually perpendicular p orbitals in our blue structures. So what's our problem? Well, we've got a couple of them. If we use the 2s and 2p orbitals in carbon for bonding, we're going to have two different types of carbon-hydrogen bonding. And we also know that our 2p orbitals are perpendicular to each other, which is 90 degrees, instead of that tetrahedral angle, which is 109.5. So what carbon does is it forms four equivalent atomic orbitals, which are all arranged tetrahedrally. And that'll give us a molecular shape, which is tetrahedral. So the 2s and the 2p orbitals must combine together. So over on the left-hand side, we have our 2s and our 2p orbitals. And a process called hybridization is going to take place, where we end up with four equivalent hybridized orbitals. It's kind of a melding together of our s and p orbitals. And that's going to give us a tetrahedral arrangement. So the idea here is whenever a set of equivalent tetrahedral atomic orbitals is required for an atom, the model must adopt what we call an sp3 hybridized orbitals. And we say that the atom has become sp3 hybridized. So if we look at our methane molecule now, we've got our carbon in the center of our molecule. It has four equivalent sp3 hybridized orbitals. They each overlap with a 1s orbital on hydrogen, and within those overlapping orbitals, a pair of electrons is shared. Let's look at ethylene, C2H4. And if we look at our Lewis structure here, and we look at each of our carbons, now each carbon is bonded to three things, two hydrogens and the other carbon. So we're going to have hybridization taking place with these carbon atoms as well. But this time we only need three things around our carbon atom, so we'll use the s and only two of the p orbitals in carbon for our hybridization. We're going to call this sp2 hybridization. So over on the left-hand side, we've got our s and our 2p orbitals. They become hybridized. We have now three equivalent sp2 hybridized orbitals. And this is going to give us a trigonal planar arrangement. But we've got something left over. We've got a p orbital which was not part of the hybridization. And that p orbital is going to be perpendicular to our sp2 hybrid orbitals. So we would have something that looks like this. We've got that yellow plane, which shows us that the three sp2 hybrid orbitals are along the same plane, so that gives us our trigonal planar geometry. But we've got that unhybridized p orbital, which is perpendicular to that plane. So now let's look at what we've developed so far in this ethylene molecule. Each of our carbon atoms is sp2 hybridized. Two of those sp2 hybridized orbitals will overlap with the one s orbital on hydrogen. We'll have a sharing of a pair of electrons in those overlapping orbitals, and that will give us a bond between carbon and each of our hydrogens. The other hybridized sp2 orbital for carbon will overlap with the other sp2 orbital from the other carbon, and they're going to share a pair of electrons there as well. But now we need to talk about that unhybridized orbital. So covalent bonds are a sharing of two electrons, and they're called sigma bonds. But that leftover p orbital can also share electrons above and below the plane of the atom. So what we're going to look at now is what's referred to as a pi bond. So if we go back and just isolate our two carbons in our ethylene model, we're going to see that we've got that sp2 hybridized orbital from one carbon overlapping with the sp2 hybridized orbital from the other carbon, and they share a pair of electrons in that overlap. That's our sigma bond. But the unhybridized p orbitals for each carbon are also capable of sharing a pair of electrons above and below the plane of those carbon atoms. And that gives us what we call a pi bond. So we're looking at what's referred to as a double bond. A double bond consists of one sigma bond and one pi bond. And the shared pi electrons are above and below the plane of the single bond. So now if we look at our entire model, we've got our carbon atoms, which have been sp2 hybridized, leaving one unhybridized p orbital. We're going to have an overlap of a hybridized p orbital from carbon with each of our hydrogens. That gives us sigma bonds. We're going to have an overlap of an sp2 hybridized orbital for each of our carbons, which will share a pair of electrons, so there's a sigma bond. And our unhybridized p orbitals above and below the plane will also share a pair of electrons. So the sigma and pi bond between our two carbon atoms leads to the double bond in our structure. So when we talk about sp2 hybridization, we will always have this type of hybridization if there are three effective pairs coming off of an atom. So let's look at carbon dioxide. We have two different things we need to look at here. We need to look at the oxygen and the hybridization that takes place there, and we need to look at the carbon and the hybridization that takes place there. So let's start with our oxygen. Oxygen has three effective pairs. It has two lone pairs of electrons, and it's sharing a pair of electrons between carbon. So we're going to need sp2 hybridization on each of our oxygens. We're going to have a lone pair of electrons in two of those hybridized orbitals, and then they're going to overlap with the carbon to form that sigma bond. And we're left over with an unhybridized p orbital on each of our oxygens. Now let's look at the carbon. The carbon only has two effective pairs coming off of it. So we're going to have one s and one p orbital involved in our hybridization. So we're going to call this hybridization sp hybridization. This is going to leave two unhybridized p orbitals around our carbon. So when we look at the sp hybridization, we've got an s and a p orbital which will meld together to form two equivalent sp hybridized orbitals, which will give us a linear arrangement. And we're not including those two unhybridized orbitals. So if we look at our carbon, the yellow here represents the sp hybridized orbitals, and then we've got our two unhybridized p orbitals. So now if we look, we're going to have an overlapping of the sp2 hybrid orbital on oxygen with the sp hybrid orbital on carbon, and that's going to form a sigma bond by sharing a pair of electrons. The same thing will happen between the carbon and the other oxygen, where the sp2 of the oxygen and the sp of the carbon will overlap and share a pair of electrons and form a sigma bond. The two other sp2 hybridized orbitals on oxygen will be occupied by lone pairs of electrons. Now we want to talk about the unhybridized orbitals on oxygen and carbon. So the empty p orbitals on the oxygen and the two on the carbons form pi bonds. So we're going to have a sigma bond and a pi bond forming between each oxygen and carbon, which leads to a double bond. So in carbon dioxide, our oxygen is sp2 hybridized, two lone pairs of electrons and a sigma bond. Our carbon is going to be sp hybridized, two sigma bonds to each of the oxygens. And then our unhybridized orbitals are going to lead to the double bonds between each of our oxygens and carbon. Notice that the double bond consists of one sigma bond and one pi bond. And that's our definition of what a double bond is. So now let's look at nitrogen. If we look at each of those nitrogens, there are two effective pairs. There's a lone pair, and then we've got a bond between each of the nitrogens. So this time, we're going to have sp hybridization for each of our nitrogens. We're going to have each nitrogen containing a lone pair of electrons in one of those hybrid orbitals, and a shared pair of electrons when the sp hybridized orbitals overlap between each of the nitrogens, and that's going to give us a sigma bond. But we're going to be left over with two unpaired or unhybridized p orbitals. And what that leads us to is a triple bond. A triple bond consists of a sigma bond and two pi bonds, which form between two sets of unhybridized p orbitals. So now let's look at phosphorus pentachloride. So here's our general structure. If we look at carbon, we've got chlorine, we've got four effective pairs. One bonding pair and two lone pairs of electrons. So we're going to need four equivalent hybridized orbitals around carbon. If we look at phosphorus now, we've got something very different. In phosphorus, we've got 5 bonding pairs of electrons. And when we need 5 bonding pairs of electrons, we're going to have to incorporate our d orbitals. So phosphorus is going to be dsp3 hybridized. We're going to continue this PowerPoint on our next slide.